Joda, am I audible to you?
Yes, ma'am.
Please share your presentation.
Host is disabled. Please enable the share screen option.
Okay, you wait 1 minute.
Okay, thank you, ma'am.
Now can you try?
The same message is also appearing on the screen.
Okay, is it possible now?
Yeah.
Okay. Joda, have you shared your screen?
Yes. Just a second, ma'am.
Yes, your screen is in the sharing mode. Please make it in the slideshow pattern.
Ma'am, is it visible?
Yeah, it's visible. Make it. Can you please enable the slideshow?
Okay.
Okay, Joda, your time starts now.
Okay, thank you. Good morning. Myself, Jauda PP. Today I will going to discuss dynamics of a two-parameter family of maps with constant center. First, we will go through some basic definitions and symbols. F is a continuous function defined on X. A point X in X is a periodic point of period N if Fn of X is equal to X and Fk of X not equal to X for K less than N. Fn of X means f of X as N times. Z of F is the set of all zeros of F, that is set of all points in X such that f of X is equal to 0. Pn of F is the set of all periodic points of order N. P of F is the set of all periodic points of F. F of F is the fixed points of F, that is the periodic points of order 1. OF of X is the orbit of X, that is the set of all points of X, f of X, f of X, etc. Next one is a symbol that symbol notates for F is topologically conjugate to G, that is H of F of X is equal to G of H of X. The two-parameter family is defined on closed interval 0, 1 for all a greater than 0 and b belongs to R. FAB of X is equal to X by X plus 1 minus X into e raised to X into e raised to A into X minus B. From the definition itself, we can see that FAB of 0, that is the image of FAB of 0 is 0 and image of 1 is 1 and image of B is B. So the fixed point of FABs are 0, 1 and B. Now to the properties of FAB. The first one is the nth iterate of FAB of X is equal to X by X plus 1 minus X into e raised to A into summation K from 1 to N minus 1 Fn of X minus B. The second property is that FAB is topologically conjugate to FA 1 minus B by phi, where phi of X is equal to 1 minus X. Now to the critical points of FAB. When we equate to see the critical points of FAB, we will equate FAB dash of X is equal to 0 implies AX square minus AX plus 1 is equal to 0. That will implies X is equal to A plus or minus root A square minus 4A by 2A. then we will get x is equal to 1 by 2 plus or minus k, where k is equal to root of 1 by 4 minus 1 by a. Then the critical points are x1 is equal to 1 by 2 minus k and x2 is equal to 1 by 2 plus k. As a goes to infinity, k goes to 1 by 2, then x1 goes to 0 and x2 goes to 1. The orbit of x, if x belongs to open 0, 1, then if b less than 0, then the orbit of x goes to 0. If b less than 0, then x minus b is greater than 0. Then a into x minus b is greater than 0. Then our FAB, that is x by x plus 1 minus x into e raised to a into x minus b is less than x, that is less than 1. Then we will get, right, the nth iterate of f of x is always less than or equal to n minus 1th iterate of f of x. So that implies fn of x goes to zero. Similarly, if b greater than 1, then fn of x goes to 1. Now, if b is in between 0 and 1, b is in between 0 and 1, then we know that FAB is topologically conjugate to FA1 minus b. Then it is enough to study about the properties if b in 0, 1 by 2. That if 0 less than b less than 1, then the fixed points of FAB is 0, b, 1. FAB dash, that is the derivative of FAB at 0 is greater than 1. Similarly, derivative of FAB at 1 is also greater than 1. So we can say that 0 and 1 are the rippling fixed points. Now the b is also a fixed points of FAB. It is repelling or attracting fixed point according to the value of a. That is, if a is greater than 2 by b into 1 minus b, then it is repelling. Otherwise, it is attracting. If 0 is in open, if b is in open 0, 1, then x is a periodic point of order n, then we can say that b is equal to the arithmetic mean of the first n iterates of f. If x is not a periodic point, then b is equal to limit n goes to infinity 1 by n summation k from 1 to n FAB raised to k of x. If b is equal to 1 by 2, then from the above, 0 and 1 are the repelling fixed points of FAB. B is repelling fixed point if a is greater than 8. A is less than or equal to 8, then B is an attracting fixed point. These are my references. Thank you.
Okay, any questions from the participant side? Okay, thank you, Jodha, for your presentation. Can you please stop your sharing the screen? Okay. Next presentation is by Jiva Jose, presentation number CP29. Jiva, can you share your presentation?
Okay.
Please enable the slideshow.
Is it okay, ma'am?
Yes, you can start your
Shall I
presentation.
start? Okay. The topic of my presentation is on the space of generalized persistence diagram. So needless to say, persistence diagrams are important topological summaries for topological data analysis. And this entire process starts by constructing a topological structure on a set of data points. And for that, we need building blocks called simpliciters. And simplices are basically generalized triangles. And with the help of these simplices, we can construct complexes called simplicial complexes under certain conditions. And there are different ways to construct it called linear complex, Cache complex, Phillips complexes, etc. Now, once we have a simplicial complex, we can collect all p simplices and consider their linear combination, and we call it a chain. And set of all p chains forms a group. And so we can then define a homomorphism from one p simplex to its p minus 1 faces. And the chain with zero boundary is called a cycle. And fundamental lemma states that all boundaries are cycles. So it is essential to distinguish between real cycles from that of boundaries. For that, we define pth homology group. And pth Betti number is defined to be the rank of pth homology group. And it basically gives the number of p-dimensional halts present in the simplicial complex. Now, a subcomplex means a complex that is present inside another complex. So, in the data analysis process, as parameter changes, we'll get a nested sequence of subcomplexes like this. If Ki is a subset of Kj, then we will have an inclusion map I from Ki to Kj. And this inclusion map will induce a homomorphism Fpij from the pth homology group of Ki to that of Kj. Now, if we have such homology groups and homomorphism between them, we can define what is a pth persistent homology group, and it is defined as the image of Fp of Ij. Now, the rank of this pth homology persistent group is called the pth persistent Betti number. Now, if we have a class, there is a birth time and death time associated to it, and based on that, we can define what is the persistence of homology class born at Ki and by entering Kj, and it is J minus I. Now, once we have all these details of persistence, we can visualize it using different techniques, and one among them is barcode. A barcode is graphical representation of persistent homology as a collection of horizontal line segments in a plane. And just we can see here, the horizontal axis corresponds to the parameter and the vertical axis corresponding to the homology generator. Another way of representation is persistent diagram. In persistent diagram, we represent this information in the form of points, Ij, where I denote the birth time and J denote the death time. And mu Pij is the number of multiplicity of point Ij present in the persistent diagram. So basically, persistent diagram is a multi-set of points Ij with multiplicity mu Pij. Now, fundamental lemma of persistent homology will give a way to calculate the pth persistent Betti number with the help of multiplicity of points. Now, for further statistical studies, persistent diagrams are represented in different ways. In this paper, persistent diagram is defined as a function from a countable set I to this particular set, that is set of all R2 above the diagonal line. Now, if we have two persistent diagrams D1 and D2, we can define a partial matching between this diagram. It is defined as a bijection F from I1 dash to I2 dash, where I1 dash is the subset of I1 and I2 dash is the subset of I2. Now, in this case, we are considering the infinite metric. With the help of this metric, we can calculate the distance from a point A to the diagonal of the persistent diagram. Now, in this condition, we can define what is the cost of partial matching. It is defined as the LP norm of the distance between matched pairs and the distance between unmatched pairs and the diagonal in R2. And if P equal to infinity, we are taking the infimum norm of these particular pairs. Now, if we take the infimum of the cost of partial matching, what we get is the P versus chain distance. And when P equal to infinity, we will get the bottleneck distance. So set of all persistent diagrams endowed with these two matrices forms space of persistent diagram. And space of persistent diagram has these properties like completeness, separability, isometric embedding to separable bounded metric space, contractibility, homeomorphism to the space of finitely sequences, it's not compact, and can be written as a countable union of compact subsets. So these are the existing properties. Now, in our case, we define persistent diagram in a generalized way. So here, instead of taking points from R2, we take an arbitrary set X, and we are going to define what is a diagram on X. It is defined as a function from X cross X to Z plus union Z0. And the associated label diagram is defined as a subset of X square cross Z plus union Z0. So this associated label diagram has points Xi and denoted by X bar and Y bar. So if X bar is a point in the associated label diagram, its norm is defined as the distance from X to diagonal of the persistent diagram. And distance between two X points, X bar and Y bar, is defined as the distance of X and Y in the set X. Now, we have label diagrams. The partial matching is defined as a subset of D1 bar cross D2 bar, satisfying this condition. That means corresponding to every point X bar, we are associating a single point Y bar in D2. And similarly, corresponding to any point Y bar in D2, we are associating a point X bar from D1 bar. And for this partial matching, we can define the cost of partial matching in this way. And the Wasserstein distance is the minimum of this cost of partial matching. So the result is that if we consider set of all diagrams on a set S as ds, and if D is a metric on S square, then the distance that we defined just above will form a metric on the set of all diagrams ds. In order to prove the function is metric, we need to show symmetricity, positive definiteness, and triangle inequality. And symmetricity and positive definiteness is almost trivial, and the triangle for proving triangle inequality, we require this particular definition. And this definition show how we take composition of two partial matching, and is defined as a subset of M bar XY consisting of elements X bar Y bar such that there exists a Z bar in D Z bar such that X bar Z bar belongs to M bar X Z and Z bar Y bar belongs to M bar Z. So we can define composition of partial matching in this way. Then from that we will get the triangle inequality. And this is definition of K prism. K is a positive integer, and we say that the metric space XP has a K prism for any for any finite set F subset of X, there exists a function T from F to X satisfying these three conditions. And for any integer K, we say that F is K diagrammable if there exists a metric on X square in which the K shell around the diagonal is unbounded. K shell means set of all points that are at a distance K from the diagonal. So such a metric is called a diagram metric, and we call a set as diagrammable if it is K diagram, or if we are able to find a K metric for that set. Now the result says that DS is a set of all diagrams on a K diagrammable set S with a diagram metric D, then the space DS endowed with the metric Wasserstein metric as K prism. And these are my references. Thank you.
Any questions from the participant side? Okay, thank you, Jiva, for your presentation. Please stop sharing your screen.
Okay, ma'am.
So the contributory paper session 6 is over now. Next session will start at 10 a.m. With a talk by Amit Chattopadhyay, IIT Bangalore, on computing topological distances between multivariate data. So for that, you have to log in through the main Zoom meet link that is provided in the schedule. So thank you all.